Hey, welcome back. Mr. Richardson here with you. Ready to dive into our second unit in this chapter. We're going to look at some triglycerides today. And so here are the notes for that. This is 1.2, and today we are going to look very specifically at triglycerides. So starting off, kind of a brief overview on lipids. So our whole chapter, unit 1, is over lipids. So lipids are a pretty diverse group of macromolecules. And I say that because over the next couple of units, we'll talk about the other macromolecules, that being nucleic acids, proteins, and carbohydrates. And when we're talking about each of those, we'll see that they're all pretty similar. They're pretty similar structured. Their monomer unit is pretty much the same. But lipids are a more diverse group. Triglycerides and phospholipids, we'll spend the most time with them. Again, today we're doing triglycerides. Those two are pretty similar, fairly similar. And then there's steroids, which are, I don't know, not they share some qualities with these two, but otherwise they don't really look that similar. And we won't spend that much time with steroids. But that is our category of macromolecules that we call lipids. And today, specifically, we are looking at getting my L in glycerides, third time today so far. So triglycerides, also known as fat. So to the layman, to you, more than a few minutes ago, triglycerides are commonly referred to as fat. So they're made up of a glycerol and 3 fatty acids. So a lot of times we have these big, long words, complicated words like triglyceride, and we use that in biology. But when you really break it down, a lot of times they make pretty good sense. Tri, like triangle, has 3 angles. Tricycle has 3 cycles or wheels. So tri for the 3 fatty acids, and then glyceride because they're attached to a glycerol. So the word itself kind of tells you what you're working with when you break it down and look at the component parts. So start by looking at the glycerol. So that looks like this. We've got a 3-carbon chain, and each of those carbons has an OH coming off of it, a hydroxyl group coming off of it. So this is our glycerol. And just a little bit different than that. Whoops, wasn't on the camera. There we go, fix that. So a little bit different than our glycerol is a fatty acid. And fatty acids are really comprised of two parts. So the first part here, kind of a dotted line around this area. And this area, kind of on the top or on the front, is known as a carboxylic acid. Has the carbon kind of double bonded to the O there and single bonded to an OH. So that's a carboxylic acid, and that's important because that's where the fatty acid is able to connect to the glycerol. And we'll see that in just a minute here. The rest of it then is a long chain, a long tail. Ours is actually pretty short, really. So most of these fatty acid chains are between 12 and 18 carbons. In fact, I've most often heard they're 16 to 18. So I don't even know if 12 is within that range, but certainly fits. So 12 to 18 carbons. Ours has 1, 2, 3, 4, 5. So 5 carbons. Ours works. The smallest chain I've ever heard of has 4 carbons in it. And the largest, as far as I'm aware, has 32 carbons in it. We're not going to fill up our page with 32 carbons. In fact, we didn't even get to 12, let alone 18. But this one works because, again, the smallest one has 4. And there we go. So this is a very small fatty acid chain. And these fatty acid chains so they can be what we call saturated, like the one above, where it has all single bonds. All these carbons in the fatty acid tail have single bonds. Don't worry about the carboxylic acid. I know you'd say, it's a double bond there. It is, but they all have that carboxylic acid in the top, so it's after that double bond to O. What do we have? All single bonds. Or, so that's called saturated, excuse me. That's called saturated. And the reason why it's called saturated is because it is full of hydrogens. Every carbon has as many hydrogens on it as it can possibly have. It is full or saturated with hydrogens. The other option, if they aren't saturated, they're generally if they aren't saturated, they tend to be unsaturated. And there they have at least one double bond. Now that's going to be a really, really important concept. And I'll show you why, or attempt to show you why. So my next fatty acid now don't draw this yet. You sit tight, you watch for a second. I'll tell you when to draw. You may have to pause the video, but hang on just for a minute here. I'm going to do a little bit of erasing. All right, so we have a fatty acid. And in order to make 2 of these carbons double bond, what we're going to need to do is take away 2 of the hydrogens. And that's why it's called unsaturated. It is not full of hydrogen. It could hold more. So now that these 2 carbons are able, they have room for another bond, imagine we have to kind of pull this chain down so that it's close enough to connect these 2 with the double bond. So I'm going to go ahead and erase the end of my chain now. and my double bond kind of bends. Again, I had to bring that other carbon down here. And that provides a bend, what we call a kink, in our fatty acid. It's now bent, it's kinked. Again, notice we've got one less hydrogen on each of these carbons. That's why it's not saturated or unsaturated. And that kink is super, super, super important in biology. It has a lot to do with what's healthy and what's unhealthy, and how fluid your cell membrane is. So because of that kink, unsaturated fatty acids can't pack this tightly. Those kinks kind of kick other tails, they kick other fatty acids, they kind of keep them separated. So they're a lot less dense, which means they end up being liquid. Normally, we think of unsaturated fatty acids as oils, vegetable oil, canola oil, olive oil. They're all unsaturated fatty acids, and they're generally considered healthier for you. All because of that kink that you saw on that last page. Saturated fatty acids, on the other hand, so they're packed much tighter because they're all straight chains. They pack, they fit nicely, they pack together. That makes them much more dense. And so these tend to be solids. Think of butter. Butter is generally saturated fatty acids. Again, those tails are perfectly lined up. They fit in nice and tight together, which makes them dense. And these are generally considered not as healthy. That's not as healthy for you. So that double bond, that unsaturated fatty acid, that double bond, that kick, that kink, it really, really makes a big difference in what type of fatty acid you end up having. Let's take a look at the synthesis of our fatty acids. So again, here's our glycerol. Kind of turned it on its side here from the way that we had it before. So it's a 3-carbon chain. Each of those carbons has an OH on it. Here's our fatty acid tail. And what we have happen is this OH and this H joined together. They're actually going to end up leaving. We'll draw that in just a second. And then this O right here from the carboxylic acid, this O takes that O spot, and he ends up connecting to the carbon of the glycerol. And we end up with, if we have enough room left, get kind of tight. Here's our glycerol. And again, these bottom two, we didn't change. So they're still going to have an OH on them. But it's this top carbon that is now bonded. So there's the O. But it's this O. It's the O that's a part of the fatty acid. And now that chain should get all those hydrogens on there. Now that chain is attached to the glycerol. That fatty acid is attached to the glycerol. And what else did we make over here? O and two H's, well, we all recognize that. That's water. Water comes out of the reaction. Water is formed. These wasted parts, if you will, come together and like, oh, we're going to be together, and they end up forming a water molecule. And overall, this is called a dehydration synthesis. And the reason for that is that there's a loss of water, dehydration. We're synthesizing or making something. We connected that tail onto the glycerol. Water came out. Water was lost, so dehydration. So dehydration synthesis. And that's how we make our triglycerides. Now keep in mind, if you're going to make a full triglyceride, you need to add two more tails, two more fatty acid tails, and so two more waters would come off. We just saw one, but again, connect another tail here and another tail there, and you'd have yourself triglyceride. Let's wrap these notes up here and finish up what we're thinking. Triglycerides Triglycerides are excellent at energy storage. They actually store twice as much energy per gram as a carbohydrate. So pound for pound, these guys are twice as good, 2 times good as sugar and other carbohydrates. It stores a ton more energy. For animals, for us, this is good. We're mobile. We have to be able to carry around our energy with us. So we want something that's efficient. Plants, they don't really have to move. They just have to grow big and tall. They can stay put. Plants tend to store their energy a little bit more in carbohydrates. Again, the reason for that is they don't particularly care if they're heavy. In fact, heavy might even be an advantage for them to be big and thick and store their energy in this clunky carbohydrate. But for us mobile animals, we want to be able to carry our energy on our back or on our belly, as it were. And so we use triglycerides. All right, the fourth time misspelling that word, I apologize. So animals, we store our triglycerides, what we call adipocytes, which are fat cells, and they're created in the liver. And what these are basically is just a cell. So imagine your membrane-bound cell, and it's just filled with triglycerides. It's like a bubble full of triglycerides. So that's where we store our triglycerides, our energy. Plants, just a little bit different. So plants don't use triglycerides nearly as much as animals do, but they do use them to pack their seeds. Again, their seeds are what is going to grow into a new baby eventually, almost the equivalent of like an animal egg. And they want that new plant to have all the energy it can possibly have at the start of its life. So plant seeds tend to be packed with triglycerides. So that's the main spot that plants are using those. All right, well, I think that finishes up our notes on triglycerides. So I will end you there, and hopefully this all makes pretty good sense. Shoot me an email if it doesn't, but otherwise I'll see you guys for our next recording. Have a pleasant afternoon.